Welcome back. Before we move on, I just want to go back to the point of confusion I created when I said something and then wrote something else. I want it to be clear. We're comparing these three carbons, this one right here, this one here, and this one here, to these three bonds to carbon. This one here, this one here, this one here. We're trying to decide the 2 versus the 3 issue. Of those 3 dots of carbons that we're tied all the way up to, which one of those 3 carbons has the heaviest thing attached? Because that's what you always compare. So this carbon has a fluorine. What's the heaviest thing on this carbon? Don't go back. Always go away from the stereocenter. It's another carbon. Well, fluorine beats carbon. What's the heaviest thing? Don't forget, you're still going away from the stereocenter. You're comparing an H to an F. Well, that's even this one, you could have just stopped after this because this had the highest priority, better than this carbon down here that has 2 H's. Okay. So that explains the 2 and 3, and we're ready to move on again. And here's the deal. We're supposed to draw all possible stereoisomers of 1,3-2,2-dibromovinyl, 1-cyclopropyl cyclopentane. It's a mouthful. Start off at the end and draw cyclopentane. That's 5 carbons in a ring. Pick a carbon to be carbon 1. Here, I'll do it on the left side. And on carbon 1, I see there's a cyclopropyl. So off carbon 1, I need a triangle whose corner carbon is attached to cyclopentane. Remember, cyclopropyl, all 3 carbons are part of the group. And that means this carbon can't be this carbon. All right. On 1, there's this die means there's 2 identical groups. Do you know how I know that? Well, when I see a die here and 2 numbers in front, it means 2 identical groups. And the group is a vinyl group. So I draw that first. On carbon 1, there's a vinyl. And I'm going to do the same group on 3. On the vinyl, there's 2 bromos off of carbon 2. This is carbon 1 of vinyl. In a group in parentheses, carbon 1 is the one attached to the chain or the ring in this case. There's 1. There's 2 fluorines up here. I'll tell you what students have drawn. I'm not even going to write it because I don't want an image of it in your brain. But I've seen students right here just write F2. Right there. You've just changed the end of the label here from a C, which you need as part of a vinyl, and you got rid of it by just writing F there. Don't do that. You have 2 options. You could write CF2. That's one option. Or you can draw the 2 bonds to F. Oh, don't do this either. I mean, this is fine. This is what I want. I'm drawing it. I want it. That's one way. But I've seen students draw a single bond, and on the end of it, they write F2. Not acceptable. The only way that would work is if there's a bond to F, and then the F has a bond to F, and that's not what F does. Show me you know what F does. Okay. So I didn't want it on the page that there's. So you have a visual, because some people just remember the visual even when it's wrong. In many videos I say it, I write it, and I don't know if it's working. Anyway, we had a question.
Shouldn't the F's be bromines?
You're right. I'm going on, and I got to read my own question a little better. I had fluorines in my mind, I guess, from the previous question. They are bromines. It says dibromovinyl. Yeah. But everything I said about F is good for Br as well. That's one way to do it. Do you want me to do it the other way over here? Just to show you, you can write Br too, but you better write C first. There's a way to do it. Those are both the same group. I hope you know that. And the stereocenter on 3, to do a proper stereocenter, you need to number the 4 different substituents. You better draw them. That implies that if there's an H on a stereocenter, like there is on carbon, this is carbon 3. This is carbon 3. There's 1, there's 3. You better draw the H. Now it's time to put wedges and dashes, because if you don't, you've just wasted all your time. If I don't see proper tetrahedron, then don't even start this question. So you have to have proper tetrahedron. It's better to have a proper tetrahedron and determine it, the R or S, wrong than to not even have the tetrahedron. You won't get points for anything if you do that. So here we go. We've got a stereocenter on 1. I'm just going to give you the priorities here. I hope you can catch up later. The 4 is here. The 3 is here. Both of these C's have 2 more bonds to C and a bond to H, so they're tied. So I go to this next C, and you go to this next C and ask the same question I asked earlier. Next C, same distance from the stereocenter. Which one has the heaviest atom? Br. Heaviest thing here is another bond to C. Yeah, you're going away from the stereocenter. Br beats this C. Okay, so we have a winner for 1 up there. And a 2 here. Do yourselves a huge favor and put the 4 on a dash. You don't have to, but why not? You could put it on a wedge just to be cute. I don't mind. I'm going to grade whatever you give me. I'm going to check it. If it's right, you get points. I give you strategies, you know? You don't have to use mine. There's many ways to draw these molecules properly. All right. Now I've got the 4 on a dash, and I have a wedge on an adjacent bond, and 1, 2, 3 is counterclockwise. You need to say S near your stereocenter. Just put it right there on top of your stereocenter. Moving on to the other stereocenter. We'll do it in, I don't know, pink. We have a 1 with a C that has 2 more bonds to C. Neither one of these does. 2's here, 3's here, 4's here. And we're going to do ourselves that big favor again and put the 4 on a dash. And an adjacent bond on a wedge. I won't even grade the fact that you drew something that's somewhat impossible here. If you've got this bond underneath the page, this carbon beneath the page, and this carbon in front of the page, they really can't reach each other. But I'm not going to even grade that. No, you're fine. Leave this. I love it. If you tried to make the toy like this, you said that you can't have a bond to a carbon behind and in front in the ring that's this small. Anyway, we do, and we don't care. We're going 1, 2, 3, S for the stereocenter as well. There we go. And we're going to draw the mirror image because it's a quick way to do the strategy. There are 2 mirrors here. Looks like goes Br2 to C. Double bond to C to a ring. How's that ring looking? The ring, that wedge is just leaning a little towards the mirror. This goes away from the mirror. The dash is leaning a little away from the mirror. Goes up to a corner. The wedge is definitely down and away from the mirror. The normal bond is a little away from the mirror. Put it in green. A little away from the mirror. Up. And I don't know. Which one do you prefer? The CBR2 way? There, I got them both the same way on this one. Okay, we need that H though. That H is on a dash from this carbon towards the mirror and down. You don't have to show me 1s, 2s, 3s, 4s. The mirror image of the pink S is a pink R. The mirror image of the blue S is a blue R. You don't need to use colors on your test. There you go. I didn't draw a cyclopropyl, though. Somebody's going to point that out. I'd dock you probably, if this was the only time you did it, a 1/4 point here, because that's not a cyclopropyl anymore. I understand mistakes happen, especially when time is a factor. That's why I'm not overly strict. Unless you drew it wrong every time, then what can I do, right? Okay, just want to make sure that wedge goes all the way to the corner of the triangle. Now, what's my strategy for drawing molecule number 3? Well, I'm going to copy molecule 1 right under it. On one of the stereocenters, I am going to do a single switch. Try my best here. I'm going to leave the cyclopropyl out here. So I'm not going to touch this stereocenter. And this goes to CBr2. And I'm going to switch the H with the CBr2. So on my dash, sorry, CCCBr2. A little lazy describing that there. And the H will stick up here on the same bond. We did a single switch on a stereocenter. Single switch on a pink S gives us a pink R. No switch at all on the blue state S. Draw the mirror image and be done. Well, 6 points away from done. 6 points in 6 seconds away from done. Oh, maybe we should even check that with a clock. All right, carefully, faithfully, with high fidelity. Copying mirror, or doing mirror images. Not quite copying, is it? And I could have, used the same strategies above and say, I just did a single switch on the same stereocenter here. That's another way to approach it. And we get that. Don't have the H. Did I do a good job? Away from the mirror and up, away from the mirror and up. Doesn't matter if this is pointing left or right. It's not a stereocenter there. It's this one. Yeah, pink R mirror image is pink S. S. Blue R mirror image is R. And can we get 6 points in 6 seconds? Put the clock on. E. Yeah. If I don't speak, maybe. I think it's going to be closer to 10. These are diastereomers when only one of the stereocenters is different. Enantiomers have both stereocenters different because they're mirror images of each other. And that was 6 points just for the E's and D labels.
Professor?
Yes.
So I was doing it as you were going along. And then so for when I switched my stereocenters, I put my H on a wedge, and then where the wedge you have it original like on the bottom left, I had that as a dash. Would that be wrong or
Put
no?
the H here and the carbon out here?
Under that one. When we had to change it to R.
Well, it's just hard to switch this with something when you have to redraw it.
Oh,
I wouldn't pick the ring carbons to do switches with, just the outside the ring. It's just more convenient.
no, I'm talking about for the diastereomer.
Oh,
On the
going
bottom.
down here? Oh,
Yeah.
oh, you know what I'm thinking you're saying? Yeah, this is another, I didn't teach this strategy. It's a great strategy. I'll show it to you real quick. You might like it. Oh, can't do that. I want my molecule. It won't let me get that molecule, will it? See what it gets. There's a little incidental stuff. Okay, there's a lot of incidental stuff. All right, let's get rid of it. Oh, thank you. All right. So I did a literal copy, didn't I? And another way to accomplish a single switch, and I think this is what I've had his permission to use his name from before. I'm assuming I still do.
Yeah, you're good.
Yeah, it's Hassan has told me that I believe he did this. So doing a switch of something that used to be a bond that was a dash to a bond that's now a wedge is a single switch. This qualifies as a single switch.
Okay.
It does. And you'll notice the stereo center is different. You know it's not S because the 4 is on a wedge, right? Look at that. And we knew a single switch switched to stereo center all along, but you can even verify that since we did this neat little copy paste job. And I didn't get my BR2. Probably wouldn't have heard the end of that. Okay. Yeah. If you think about it, we're talking about this molecule and this molecule. It's a matter of perspective. If you rotate this molecule like just a few degrees this way or this way, all of a sudden this will end up to the right side of your eye and this will be to the left side of your eye, which is kind of what we're doing here. And yeah, and accomplishing a single switch at the end. Another, just to summarize, there's another way to do a single switch. Just redraw the molecule. Where there was a wedge, make it a dash. Where there was the dash, make that a wedge.
Okay, so
that is a single switch. Just trust me. Every time will be opposite stereo center of the one you drew first.
Okay.
So good question. And if you like that technique, it's a nifty one. All right. So we good?
Yeah. Thank you.
You are welcome. I will post these after having a snack.
Thank you, Professor.
You're welcome.